Hello and welcome to Bay College's online lecture for intermediate algebra. Today we're going to look at section 8.5, which deals with the properties of logarithms. Now, before we look at the properties of logarithms, I just want to say you really need to know your rules of exponents, because as we've seen in the previous section, logarithms are the inverse operation of exponents. And whenever we have inverse operations for addition, such as subtraction, they all follow the same rules. Multiplication and division, they all follow the same rules. Exponents and logarithms follow the same rules. So if we strengthen our rules of exponents and know them inside and out, it makes our rules of logarithms that much easier because we already know them to some extent. So let's start out by looking at some rules of exponents. If we have a to m times a to the n, they have the same base. Our rule of exponent, called the product rule, says I can just add the exponents. A to the m plus n. Well, this is the same rule that applies to logarithms. Since logarithms are the same thing as exponents, right? This value is an exponent of a. We can write this as the sum of logs, okay? Log base a of x plus log base a of y. Why can we do this? Well, here we have a product. Here we had a product. We could write this product as the sum of the exponents. Well, the base, notice the base never changed. Does the base ever change here? No. So when we have a product, we can write it as a sum. It's the same rule. So let's actually apply this rule. In this example here, I have log base 10 of 0.02x. This is a product. So I can rewrite it as log base 10, because that's not going to change, of 0.2 plus log base 10 of x. Log base 10 of x. We can split these up because the product rule says I can write that as the sum of logs. Now this might be something I can throw into a calculator, and now I just know a actual real value term and the variable term. So you can see where maybe that has some usefulness. What about something like this? If this was multiplied together, of course it's going to be a very huge number, but let's say we have this, maybe we factored it down to this. Let's rewrite this. This is where logs, the rules of logs can be very useful. If I can rewrite this as the sum of logs, because we do have multiplication, maybe we can simplify it and recognize, hey, I know that 8 is 2 to the third power. Log base 2 of 2 to the third power is 3. This value is 3. It's mental math now. And if I think about it even further, well, 64 is 8 times 8. Well, I can split this up even further and say log base 2 of 8 plus log base 2 of 8. Essentially, I can say log base 2 of 8 and added 3 times, well, that's 3 of those. Well, if this equals 3, what's 3 times 3? 9. So we can actually use this rule to break it down, break it down, break it down, and then just do some mental math. All right, let's look at the next example. Here we have the quotient of two bases and their exponents. Well, this is our quotient rule of exponents. Whenever we have division of these numbers that have the same base, we can just simply subtract the exponents. The top value minus the bottom. Order is very important, right? Because we have that sign. We don't want to make a sign error. It's m minus n, the top minus the bottom. That applies to logarithms. Here we have the quotient, so we can write it as the difference of logs. Opposite operation, right? Instead of multiplication like we just seen, we have division. Opposite operation. So instead of addition, we have subtraction, the opposite operation. So here, since we have division, we can split it up as a difference of logs. The base never changes. And it's always the top minus the bottom, the top logarithm minus the bottom. So log base a of x minus log base a of y. Split it up. So let's apply that right here. I see I have a quotient, so I can rewrite it as the log base a of the top minus log base A of the bottom. So maybe this is, we break it down. Maybe if we do A, we can simplify it even further, but we're just applying the rule right now. Now there's one more rule we're going to look at, and that's called the power rule. Whenever I have a base to a power raised to a power, it's called the power rule, right? Exponent raised to an exponent. Hopefully we recall that we have to multiply them. So I'm just multiplying the powers. Well, we discussed in the last chapter that a logarithm actually tells me what a power is. And here I have a logarithm raised to the value raised to some power. And then in this variable we used r. So what I can do is I can multiply it. If this log base b of x tells me a power, I need to multiply my powers. That's what I did here. So essentially, I'm going to say r times the other power, which is log base b of x. Kind of a shortcut way of thinking about this is that whenever you have a power out here, bring it out front. We're going to multiply it because this rule says I can multiply it. All right, let's look at an example where we can apply the power rule. Hopefully we remember all about radicals from previous sections. Well, before we can actually do this, there is a step we have to do. We have to rewrite this as an exponent. Well, a square root is the same thing as the 1/2 power. And now if we look at this, we can say, hey, this value is being raised to a power. I can apply my power rule and multiply it. So I get 1/2 times log base b of a. So we actually got rid of that radical and brought that power out. 1/2 log base b. Now let's look at an example where we apply all of these rules all at once. Here we have log base 10 of the quantity 5a divided by 4b squared. Now, I see I have division, so let's deal with that. I'm going to rewrite this log base 10 of 5a minus log base 10 of 4b squared. So now I don't have division. I eliminated that. I have the difference of logs using our difference of log rule. But I still have a product here, don't I? I have 5 times a, I have 4 times b squared. Well, let's split that up even further. I can write this as log base 10 of 5 plus log base 10 of a. Use that sum of logs rule. That product, I can break into a sum. Now this here's where we have to be careful, because it's minus this quantity. So if I'm going to split it up, I'm going to want parentheses in there. So I can say log base 10 of 4 plus, because this is a product, plus log base 10 of b squared. All right, lots of steps here because we're applying all of our rules in this example. Am I done? Not exactly, because I still have this power, and we have yet to use our power rule. So I can take this value and bring it out front, okay, using that power rule. Now I'm going to write it, but as I write it, I'm going to say, you know what, we can get rid of these parentheses at the same time, distribute the negative. So I get log base 10 of 5 plus log base 10 of a minus log base 10 of 4, distributing the negative to both of them, minus 2 log base 10 of b. Now, if we just assess what we did, we can actually simplify this. Log base 10 of 5, we can find that value using the calculator, minus the log base 10 of 4, a value we can find in the calculator, and we can actually combine these two now that we've done that. And then the only thing we have to deal with is log base 10 of a and minus 2 log base 10 of b. Very simple, we can isolate those variables, and that's why these rules are important. Many years ago, we didn't have calculators, and people who worked with these, whether they were engineers, civic engineers, or electrical engineers, or even sometimes you might have to deal with something like this in business. It doesn't rear its head. You'd have to use a logbook back in the day before you had calculators, and the logbook didn't have every single calculator or value on Earth. You actually had to break your logs down So you can see where this applies. Okay? So log base 2 of the cubed root of 24, let's apply these rules to this example. Now, first thing I have to do is I have to get rid of this radical. So I'm just going to rewrite it right here. Log base 2 of 24 to the 1/3 power, right? That 3 we have is our index, becomes the denominator of this fraction. That's one. So you remember that. Now, I can use the power rule, because I only have a single log here. Let's bring that power out. 1/3 log base 2 of 24. Now, I could stop there and say good enough, but I know 24 has some factors. And essentially, the factors I'm looking for, I want to see 2's, right? This is divisible by 2 once, twice, 3 times, right? So let's split this up. We have 1/3 log base 2 of 8 times 3. 1/3 log base 2 of 8 times 3. What is 8? It's 2 to the 3rd. Well, let's break up this product here. Lots of extra work we can do, but we're applying the rules. It's good exercise, right? 1/3, and because I'm breaking it up, I'm going to use some parentheses, right? Just like I did here. All right, so we're going to get log base 2 of 8 plus, because it's a product, log base 2 of 3. And now we can simplify this. What is log base 2 of 8? Well, 8 is 2 cubed, so this value is 3. Now I'm going to distribute. 1/3 times 3 is 1. 1/3 times log base 2 of 3. If we look at this, those are relatively simple numbers. If I had a log book, I could go to it and I could find log base 2 of 3. And then just take 1/3 of it and add 1. So it simplifies it. Instead of having log base 2 of the cubed root of 24, something that I wouldn't be able to find without a calculator, I can go to this. Now, oh, hey, that's a little simpler. I can find this log base 2 of 3 somewhere. All right, let's look at this example here. We're going to combine this to a single logarithm. The other ones, we had a single logarithm, and we wrote it as the sum or difference or multiples of logs. Here, we want to write this to have a single log. Well, everything we've dealt with up to this point has the same base, so we have to always make sure they have the same base. Since it's addition of logs, we know we can use the product rule, but we have this out here. This is multiplying, so I can bring it in the opposite of what we looked at in the rule. So if I bring that in, I'll just rewrite it here. We have log base e of a plus log base e of b to the 3rd power. Because of this addition, and they have the same bases, I can write this as a product. Log base e of a times b cubed. So that's a single logarithm from these two logs. Multi-steps, but we're applying those rules. Now this one here, this is going to be a long example because I'm going to show you the hard way, then I'm going to show you the easy way. Let's take all these things out here and bring them in, because this multiplication, we can undo that product rule. And if I rewrite it, I get log base 6 of x to the 5th minus 3/4, oh, I brought that in, excuse me, log base 6 of x to the 3/4 plus log base 6 of x to the 3rd power. Now I can apply my difference or sum rule here. Because this is a difference, I can divide these. Log base 6 of x to the 5th over x to the 3/4. And because this is addition, I can multiply it. And if I multiply it, I just have to bring it to the top. So now I've written it as a single log. And using our rules of exponents, we can simplify that. We know that we can add these and subtract that value. And if we do that, 5 and 3 is 8, so I have x to the 8th over x to the 3/4. 8 minus 3/4 would be 7 1/4, which is the same as 29/4. So log base 6, x to the 29/4, right? 5 and 3 is 8 minus 3/4. 7 1/4 is 29/4. So if you had $7.25 in quarters, we'd have 29 quarters. All right, and then we could do one last step to make it a little prettier. We can undo that power, right? We bring it out front. Log base 6 of x. So we took this big ugly thing with 3 different terms of containing logarithms, and we're able to use the rules and write it as a single logarithm, log base 6 of x times 29/4. So that was the long and hard way, but we used it to get familiar with our rules of logarithms. Now I'm going to show you the easy way, and it's a way you already know, but sometimes we get lost in the work and we miss some things that should be obvious or could be obvious, and I totally understand why it would happen. But let's take a look at what we have here. Here I have the same problem. 5 log base 6 of x minus 3/4 log base 6 of x plus 3 log base 6 of x. Let's just point this out for a moment. I have 5 of these log base 6 of x, and I'm going to take away 3/4 of them and then add 3 of them. Well, 5 minus 3/4 is 4 1/4 plus 3 is 7 1/4 of these log base 6s of x. Well, 7 1/4 would be 29/4 log base 6 of x. So sometimes, you know, yes, we're learning something, we're applying the rules, but sometimes there are shortcuts, and we should or could know how to do them. And maybe use that to check our work. Did we get 29/4 times log base 6 of x when we did it the long, hard way, applying our rules? Yes, we did. So let's look at one last example, or actually 2 last examples. Let's say we don't know what the base is, but we do know a couple of its values. If we allow log base b of 3 to equal 0.5, and log base b of 5 equals 0.7, can we use our rules of logarithms to evaluate other values, to find other values? Well, log base b of 25, we're asked to evaluate it. Well, let's break it down. What is 25? I'm just going to do like a reverse factor tree. Well, 25 is 5 times 5, right? And since that's multiplication, let's split it up using that product. Log base b of 5 plus log base b of 5. Well, if we return to this, hey, I know log base b of 5 is 0.7. So if this value is 0.7, I can add the same value, 0.7, and I can have 1.4. So I've solved this. There is another way to do it. I could have said, hey, this is the same as 5 squared. Bring a 2 out front. 2, and I'll do that right here, 2 log base b of 5. Well, what is log base b of 5? It's 0.7. 2 times that is the same as adding it twice. You get the exact same result, no matter what path you take to get there. Just like we've seen in the previous example, if you recognize the shortcut, it's a different path, we still came to the same answer. Now, if I look at this one here, hey, I see division there, I can use the quotient rule. Log base b of 3 minus log base b of 5. 3 over 5, use the difference rule for this logarithm. And now we can assess. We have 0.5 and 0.7. Log base 3 is 0.5, and log base b of 5 is 0.7. And we're just going to subtract these two values. That's what it says here. So 0.5 minus 0.7 is negative 0.2. So you can see where our rules can be used to evaluate functions, even if we are missing some values along the way. So this has been section 8.5, Properties of Logarithm. Thank you for watching.